It's a long talk and a short talk this session. The first talk is by Arnaud Durand on the complexity of enumeration and counting for acyclic conjunctive verbs.
Okay, so thanks for the invitation. So the talk will be about counting and enumeration in the context of logical query problem. So in counting, we have two separate but very similar problems. In counting, we try to output the number of solutions of a given problem. So classical examples are, for example, computing the number of models of a propositional formula called sharp SAT, computing the number of perfect matching in a graph. But there are also a lot of, say, hidden counting problems for which it's not so evident to see in as counting problems. So permanent, that's okay, but you also have some problems on graph and nodes polynomials and so on. So it is often a framework to discuss, to tackle a lot of problems with a mathematical flavor. So on the other side, we have a very pragmatic task. It is to generate all solutions one by one of an algorithmic problem. So it's very natural, but the one remarkable fact is that the output can be very large, and so the classical notions of complexity does not apply immediately. So in this talk, I will consider these two tasks in the context of query based on the existential and conjunctive fragments of first-order logic, namely acyclic conjunctive query. Okay, so the talk will be in two parts. In the first part, I will mainly survey, it will not be technical at all, the main complexity measure for enumeration, and look at some results concerning enumeration for query problems. And then I will conclude this part by complexity characterization for acyclic conjunctive query. Complexity characterization in the sense that I will try to delineate the frontier between tractable and very tractable enumeration problems. So on the second part, we will talk about counting and especially weighted counting. So with very different kind of techniques, this will go through some kind of original polynomial representation of query, and then consider counting as polynomial evaluation. And this time we will also try to delineate the tractability frontier for ACQ in the context of weighted counting. So although the set of results will be quite different, the common point is that in the two settings we will illustrate the particular role played by three variables in formulas. Okay. So hardness in each case will be a consequence of the topology induced by three variables. So what are the measure of complexity for enumeration? So as we know, we have to generate all solutions of a problem, so the output may be very large. So there are intuitively two sources for intractability. The first one is that we are considering NP-complete problem, for example. So it's impossible to enumerate because it's simply impossible to start. Okay. The second one is harder to illustrate. But it may happen that the difficulty comes after a certain point. So you can consider a problem for which you can say quickly that it has 1, 2, 3 solutions or a polynomial number of solutions, and then at some moment you are stuck, and then the difficulty starts here. So for tractability, the picture is more subtle in some sense. We have three main measures. The first one is called polynomial total time. This means that a problem is solvable with this measure if you have an algorithm which computes all the solutions in times which is polynomial in the size of the input and the output. So in some sense, if you don't have further information, this means that you succeed to have a globally satisfying algorithm, but you have no information on the regularity of the process. So beta is the class of incremental polynomial time in a sense which is the following. So suppose you have the input and the n first solution, then the problem is an algorithm is incremental polynomial time if it computes the n plus 1 solution in times polynomial in the size of the input and n. Okay. So it's some kind of snowball in some sense. The computation becomes harder and harder as long as you generate solution. And the base classes, in some sense, is polynomial delay. That is, a problem is polynomial delay if you can enumerate all solutions, but this time with very precious information on the regularity of the process, in the sense that you have a polynomial delay between two successive solutions. So let's take some examples. So if one wants to generate all models of a propositional formula, then it's intractable simply because it's impossible to start. It's the same for, suppose you want to compute all independent sets in a graph of maximum size. But if you change a little the notion of maximality, this time consider not the size but inclusion, then then it's polynomial delay. And it's even polynomial delay if you force some order in enumeration. So suppose that you have an order on the vertices of the graph, and then you extend this order on set of vertices to some lexicographical order. Then if you want to enumerate all maximal independent sets in lexicographic order, then this is polynomial delay. In the contrary, if you impose to enumerate for reverse lexicographic order, then it will be intractable. Simply
intractable means it's difficult to feed
to start.
NP?
Yeah, sure. Yeah, almost all results here will be modulo P different from NP, except one. So if you consider for example, generating all models of a 2CNF proposition formula, then it's clearly polynomial delay. So let's continue on this set of examples and have a look at SAT. Then there is a very classical, say, branch and bound strategy for enumerating or for deciding if a formula is satisfiable. You start from the formula, you pick a variable, you put the variable to 0 and ask if there is a solution. If there is a solution, you continue. If there is no solution, you start with, you put your variable to 1 and then, and so on. So an old result by Crenio says that in a Boolean case, there is no over efficient algorithm than the one described above. That means all cases which are easy for enumeration are precisely the case where you can apply this strategy. And if you consider CSP on arbitrary finite domain, already for CSP on domain of size 3, then the situation is more complicated in the sense that you may have enumeration algorithms which are not of this kind. So in the following, I will consider very small classes of enumeration. So we will have to look at...
Just a minute.
Yeah.
Go back one slide.
Oops. That's okay.
I mean, I find we solve by solving linear equations, right?
Hmm? Sorry.
Never mind, no, it's okay.
Okay. So we consider enumeration algorithm as algorithm in two steps. Mainly a first one called the precomputation steps, which in some sense is all the work the algorithm has to do to prepare some suitable data structure. And then once this job is done, the enumeration steps starts. The proper enumeration steps start. So in the rest of the talk, we will consider delay. We'll consider linear or constant delay, and in this context, having a robust precomputation step phase has some importance. So I will not come back on this, but space is a very important factor. I mean, the way you manage space or the amount of space you can use may give a lot of difference on what you can compute. For example, if you have polynomial delay, it can make a big difference to have polynomial delay and polynomial space, or polynomial delay and exponential space. So an enumeration algorithm will be said in, say, in constant delay. If there is some constant C, such that for all input, the delay between two solutions is constant. So use as this is quite stupid. And this means that your algorithm would be able to start within a constant number of steps from the early beginning. So we have to make this algorithm, such kind of algorithm, more robust by adding some precomputation phase. And we'll say that an enumeration problem is in constant delay with linear precomputation if it is reducible in linear time to a problem in constant delay. So you should see this kind of algorithm as a linear reduction to some basic problem. Okay, so we will consider query problem in the following. So basically the problem will be of this kind. We are given a formula in some logic L and a structure in some set of structure S. And we have two tasks. The first one is to enumerate all tuples solution of the query problems. The other one is to count this set of tuples. So it's a slightly more general problem than the model checking problem, for example, seen in the Stefan Kreuzer's talk this morning. So also, as you may have seen, there are basically three kinds of objects in these enumeration problems. You have the structure and the formula as input, but you also have the output, which can be very large. So we will consider three kinds of complexity evaluation. The first one, combined complexity, consists in taking into account these three objects in the complexity evaluation. Data complexity lays apart the formula and consider only the data and the generated data in the evaluation complexity. And expression complexity, this time consider the formula and the data. So maybe the best setting to see all these things is to consider all objects in the complexity evaluation, but accept that the formula size has a very special role in some sense. So to make some echoes to some classes seen this morning in the survey talk. For example, consider the class of structure of bounded degree. So you fix some degree, some integer degree d, and you consider the class of maximal degree bounded by d. Then first order logic on this class of structure. First order query on this kind of structure can be enumerated with a constant delay with a linear precomputation. So this fact admits several proofs, and a recent result by Casana and Seguffin shows that in fact the delay is only triply exponential in the size of the formula.
What are you counting? Is it data complexity expression? I mean, you're not saying you just data.
Data. Yeah, sure. If not constant, it will be too much. Okay. If one considers the class of structure of tree width bounded by some integer k, when enumerating the result of a MSO formula on the structure of tree width bounded by k is linear delay with linear precomputation. This is a tricky generalization of Courcelles theorem in some sense. So in the rest of the talk, we will consider query based on the existential and conjunctive fragments of first order logic. Okay, and we will consider the combined complexity of this kind of problem. So as we know, the combined complexity of model checking for this kind of formula is NP-complete, so there is no hope for enumeration as long as we consider the full fragments. So usually, if we consider combined complexity, tractable fragments can be found by restricting the formula, either by giving some condition on acyclicity of formula. This is what we will do after, or to consider some hypergraph decomposition, measure on the formula. So, okay, so I suppose almost all of you are familiar with this setting, but in the rest of the talk we will see a lot of pictures. All these pictures are associated to formulas, not to structure. So we will, given a formula, we associate an hypergraph to this formula by the following means. We consider as a set of vertices of the hypergraph a set of variables of the formula, and for each atom of the formula we associate what we call an hyperedge built by using the variables of the atoms. So in fact, we look at the formula but simply forgot the signature. So as for graph, there is a notion of several notions, in fact, of acyclicity for hypergraph. And an hypergraph is said to be alpha acyclic if you can apply the following rule and obtain the empty hypergraph. So what are these rules? You can remove hyperedges contained in other hyperedges. So this is a kind of algorithm, but you can apply these two rules independently. You remove hyperedges contained in other hyperedges, or you remove vertices that appear in at most one hyperedge. So if by applying these two rules you obtain the empty hypergraph, then you say that your hypergraph is acyclic. And of course, a conjunctive theory will be acyclic if its associated hypergraph is acyclic. Okay, so this is classical. So let's apply the algorithm to this hypergraph. I can eliminate these vertices. Now I have an hyperedge fully included in this one, so I can eliminate this hyperedge, and so on, and so on. Okay, so this is acyclic. This, I can eliminate this vertex, and this vertex, and at the end I have a triangle, and no hyperedges fully contained in other hyperedges. But strangely, if I add an hyperedges to this hypergraph at the beginning, then I can eliminate this. Then once this vertices is eliminated, this hyperedges is fully included in this one. So I can eliminate this hyperedges. I can do it with this one, and I can do it with this one. And then I eliminate the last one. Okay. So this defines a large class of hypergraph theories, and it's also the base case for more evolved decomposition methods in general for hypergraph. So there is an alternative definition of acyclicity, and this is the one we will use in the rest of the talk. An hypergraph is acyclic if, in some sense, it admits a joint tree. So compared to what you know for bandit tree width, for example, you have an hypergraph admits a joint tree if he has a tree, okay, and to each vertex of the tree is associated a bag, and in this bag you find an hyperedge. Okay. For bandit bandit tree width, the condition was you find at most k plus 1 or k vertices in one bag. Here the condition is that to each vertex of the tree is associated one edge. So it's not hard to see that an hypergraph is acyclic if it has only if it has a joint tree as an equivalent definition. So we can illustrate this easily. Suppose you have this hypergraph, and you apply the elimination rules, and while applying the elimination rules, you construct the joint tree in parallel. So remember you have two rules: the one to eliminate vertices, and one to eliminate hyperedges fully included in other hyperedges. If you use the first rule, you do nothing. If you use the second rule, then you add an edge between the hyperedge between the two you add an edge between the hyperedge included in some you have two hyperedge and one is included in the other, and you add an edge between them. So let's illustrate this. So consider this hyperedge. I can eliminate the vertex f. Then now I have this fully blue hyperedge, this blue hyperedge fully included in this one. So I will add an edge between the vertices representing this hyperedge and the vertices representing this hyperedge. This is done here. Okay, and now I can eliminate these vertices. This one is fully included in this one, so I will add an edge. Okay, this one is fully included in this one, I will add an edge, and that's over. So you can, using the elimination algorithm, you can build a joint tree step by step. So what is known about acyclic conjunctive theories? Oh, it's a well-known result by Yanakakis that you can, if you have, no, Yanakakis is for some model checking, but it's easy to generalize to enumeration, or not to enumeration, but to the problem of producing all the solution. If you have a conjunctive formula and a structure, then we can build the set of solution in time which is linear in these three entities. Linear in the formula, the structure, and the output. We can, to play a little, we can, for example, admit that the language, authorize the language to contain this equality. In this sense, in this context, then we still have a tractable algorithm, only with an exponential dependence in the size of the formula. But this is not the subject of the talk here. I will now illustrate Yanakakis algorithm, which is very classical in next slides, and show from this algorithm where is the point, where is the problem for enumerating fastly. So, okay, there is something written here, you see? No? Okay. Me neither. So here, this is the tree decomposition of the formula, and here you have an atom S depending on variable x and y, okay, and here you have an atom R depending on variable x and z. So x is the common variable used in this atom and this atom, and z and y are proper variables for these two atoms. So consider the tree, consider a leaf, consider the parent of this leaf, and then what does the Yanakakis algorithm? It applies some kind of local consistency rule, in the sense that it will filter the relation here by the tuples of its relation here, and keep in the relation here the sub-relation that can be prolonged in some sense in relation R. And when this is done, so he modifies the relation which is used here. He filters the relation which is used here to take into account this constraint. And once this is done, the algorithm continues bottom up with the new data, the filtered relation, and drops this atom from the formula. Okay, this is classical. So you will do this bottom up. Now, what is the problem so what can we say about enumeration if we consider a conjunctive query? So by applying this algorithm, we can decide if the result of the query is empty or not. But we cannot produce, we can produce, but it's quite costly to produce all the solution of a query. Why is it costly? Okay, let's consider the following algorithm, which shows that in some sense enumerating is easy, but not very fast. So start from a conjunctive query with 3 variables at the origin x1, x2, xk, and quantify variable y, and take the existential closure of this query, and then liberate one by one the variables. Okay. So what do? We liberate the first 3 variables, check if this formula, if this query constituted of, if this query with only one free variable has solution in the structure. If it is the case, then for each pre-selected solution, continue inductively. Okay, I'm not sure it's clear for everyone, more or less. Okay. So this is a kind of branch and bound algorithm, classical, inspired by the SAT algorithm I have shown right before. So if we apply this strategy, then we can enumerate all solutions of this kind of query in a delay which is linear in the size of the formula and the structure. Since there is since the number of solutions is this, the delay is this, then the total time is this. Okay. Now another situation. What happens if all variables are free, in the sense that if all variables participate to the result? Then this time we have an easy algorithm and a very fast algorithm, which consists in the following. We compute a tree decomposition. We filter each parent top-down this time, such that only tuple that can be extended to resolution remain. So we apply this kind of local consistency. And then at the end, we have a tree, and each tuple in each relation participate to one solution. So we can run through the tree and output the solution. If we apply this strategy, then this time the delay will be only linear in the size of the formula, okay, but with a linear pre-computation. So we have two extremal cases. the general case is here, and we have a delay which is linear in these two entities, or the case where all variables are free, and in this time the delay depends on the formula. Okay. So what is the problem? Suppose you have a tree decomposition here, okay, and I have made, I suppose that in blue box I have atoms using only quantified variables. In yellow box I have atoms using only free variables. And okay, in reality there should be also green boxes, atoms using both free and quantified variables. So typically, if a tree decomposition is like this, okay, that is, if the free variables are all grouped together, then the situation is very good, in the sense that we can absorb this existentially quantified, this atom made of existentially quantified variables, more or less, and then at the end it will result in a tree, in a yellow tree, containing only free variables that can be enumerated quite fastly. So this is the good situation. The bad situation is the following one. Now you have your set of free variables in two separate parts of a tree. In this case, then these blue boxes can be absorbed by this one. The blue box here can be absorbed by this one, but whatever you do, you will still have two yellow parts. And this is the bad situation. And this is precisely, this is a priori a situation where you cannot obtain constant delay. So we will make this precise and try to characterize exactly the situation where acyclic conjunctive query admits constant delay algorithm to the and the situation where constant delay where acyclic conjunctive query admits linear delay algorithm only. So to do this, we will have to make some small work on hypergraphs. So let's start. Let's consider an hypergraph representing.
Say again exactly what is the problem. What's the basic
Here, because okay, suppose the free variables are here and here. They are spread in these two parts. Here you have quantified variables. Now you want to enumerate all possible solutions. Okay, so suppose you have a value 1, you see here, and value okay, A and B as a candidate to be a solution. Then there can be several existentially quantified witnesses. Okay, but associate A and B. Okay, then if you enumerate everything, you will have repetition. Okay, this is the same. There is a clear analogy with matrix multiplication, and we will see the problem. Okay, so let's consider an hypergraph, and in this hypergraph, let's consider a subset of its vertices. And we say that an hypergraph is S-connex acyclic if there exists another hypergraph, which is an extension of the first one, but a very nice extension of the first one in the sense that all new edges are already sub-edges of the first hypergraph, in the sense that we are looking for an hypergraph H prime, which is what we call an inclusive extension of an hypergraph. Okay. And we can add, to construct H prime from H, we add hyperedges, but all these hyperedges must be already included in some hyperedge of H. And we also have this last condition that in this new hyperedge, in this new hypergraph H prime, there is a connected subset of vertices in the tree decomposition, such that the union of all vertices included in the bags of this tree are precisely the set S. So a formula will be say free connex acyclic if its hypergraph is connex acyclic, is S connex acyclic for S equal to the free variables over 4 times. So let's have a look at an example. So we start with this hypergraph here. The set of vertices A, B, C, D, A, F, and there are three hyperedge, this one, and this one. Now the set of free variables is B, C, and D. So what do? We extract from this hyperedge B and C. Okay, we extract from this one or from this one C and D. We construct a tree decomposition, and it happens that the tree decomposition here has two vertex whose bags contain the set of free variables. So technically, it's not evident how to construct this H prime, but fortunately, there is an alternative characterization. Given an hypergraph and a set of vertices, an S path will be the following. It's a path which relates, whose extremities are vertices in S, and whose intermediate vertices are vertices not in S. Okay, and such a path is an S path if, moreover, there is no edge in the average containing both X and Z. And it requires a little work to show that an hypergraph is S-connex acyclic if and only if it is acyclic and has no path of this kind. And this property can be checked in quite a lot of time. So free connex acyclicity in some sense is the fact of being grouped up to hypergraph path. So what can we do with this? Let's consider the following enumeration view of the matrix product. So we are given two matrices in some space, okay, and we want to enumerate all non-trivial coefficients of the product. Okay, so in fact, we want to enumerate all indices of non-trivial coefficients coefficients of the product. So we are given two matrices. So in a Boolean case, this amounts to solve this kind of query. Okay. And this query is precisely, in some sense, a bad query in the sense that you have two free variables here and here, and they are separated by a quantified one. And you can do nothing. You cannot make these two variables together. Okay, we have the strange S path, which is a path relating two free variables by non-free variables. So, and we can prove the following can be proved in some sense to characterize the complexity of ACQ. So, let's take an acyclic conjunctive queries and assume that the Boolean matrix product cannot be done in linear time. Sorry, or linear time in the size of the matrix. So assume that the Boolean matrix product cannot be done in times n square if you consider n times n matrices. Then one of the following two cases, hold. Sorry. Either your formula is free connex, that is you can group together all the free variables as seen before. Then in this time you have a constant delay algorithm with a linear precomputation, and the total time required to evaluate the query is additive in the size of the two. Okay. Or the formula is not free connex acyclic, and in this case there is no constant delay algorithm, okay, with linear precomputation. And in fact the best algorithm we know is the product here. So it's A times E of A. And it's okay. It can be decided. I mean, it's polynomial time to determine if a formula is free connex acyclic or not. Okay, so this is the case for. So how do we prove this? I will skip the detail. In fact, so the only things to prove is the hardness proof here. Okay. So what do? We start with two matrices, and we will try to embed the matrix product into a query problem in the following sense. So consider any kind of formula which is acyclic but not free connex. Okay, so this formula may be complicated. Okay, it can be huge. What we will do is to plug into to construct a structure such that the evaluation of the formula on this structure is as hard as the Boolean matrix product. Okay. So in a sense, the new structure will encode the two matrices, plugging with the S path. So I will not give details on this because I will come back on on a more evolved. I will show some more evolved results on using technique of this kind. So, if I summarize the situation for enumeration, there is some kind of dichotomy between tractable case here and very tractable case. And this and the criteria to determine if there is an efficient algorithm is based on the positions of free variables in the formula. So now I will switch to counting the number of solutions. So here the situation differs far more drastically if quantified variables are allowed. So Pichler and Skritek proved in last year that if you consider only quantifier-free formulas, then counting the number of solution of an acyclic conjunctive query can be done in polynomial time. If you consider formula with only one existentially quantified variables, then counting the number of solutions is sharply complete. Okay, sharply is the odd class associated to counting problems. And basically, the hardness proof is obtained by plugging the perfect matching problem inside the query problem. So, is this the end of the story for counting? Okay, there is some basic questions still unsolved. The first one is, what about weighted counting for quantifier-free ICQ? So can we add weights to and count quite efficiently in the context of quantifier-free variables? Also, some small question is, when hardness starts in some sense. So if we take two conjunctive formula and consider the disjunction or the conjunction of these two acyclic conjunctive formula, do we have can we define intractable counting problem or not? Okay. But a more fundamental question is the following. We have seen that Pichler and Skritek results shows that one quantifier is enough to design hard instances, but in some sense it's maybe not all that we can say, and more fundamentally there is maybe hope to isolate island of tractability for counting problem even when you have quantified variables. So the plan here now is to analyze again the role played by free variables in formulas and quantified variables in formulas, and see if we can chart the tractability frontier by looking only at free variables. So first problem is the weighted counting problem. So we are considering some space with a basic operation, addition and multiplication, a ring or field or what you want, and a set of finite structure of domain D. And f weight function is a mapping that maps a value in a space to each element of the domain. Okay. So for a tuple of solution, or for a tuple of element of the domain D, the weight of this tuple is the product of the weight of each element. Then we consider the following problem: counting the number of weighted solutions for conjunctive query, whose input is the following. We have a conjunctive query that is a structure and a formula, and we have a weight function, and we want to compute the sum of the weight of all solutions. Okay. Clearly, if W is a constant function 1, this is the counting problem. Okay. If W always send all elements to 1, then here we will have a number of solutions of the query. So the question we ask is, what is the complexity of this problem for quantifier-free formula? So complexity expressed either in terms of, say, number of symbolic operations or in number of bits, but in this case for spaces where iterative multiplication and addition is polynomial time. So the strategy is very simple. We will consider query instances as polynomials, but maybe not the first polynomial to which you can think. Construct efficiently arithmetic circuits that recognize these polynomials, and then evaluate polynomials to answer to those. So let's make a quick tour on arithmetic circuit. So an arithmetic circuit is a label directed acyclic graphs with two kinds of vertices: the gates of fan-in 2, which are two kind of gates. Some of fan-in 0, which are the input gates and are labeled with either constant from the space or variables, and computation gates which are fan-in 2 and are labeled either with multiplication or addition. The size of a circuit, as usual, is the number of gates, and the depth is the length of the longest path from an input gate to the output. So this is an example of an arithmetic circuit, and we say that this circuit computes this polynomial. Okay, in a sense, I hope it's correct. Now, a circuit is said to be multiplicatively disjoint if for each multiplication gate its two input subcircuits are disjoint. Okay, so if you look at these circuits, this is not the case. Take this multiplication gate, then it has two subcircuits, this one, okay, and another one here, and they are not disjoint because they share x2. So a circuit is said to multiplicatively disjoint precisely when its two input subcircuits are disjoint. So all these notions are taken from variance settings for computation of families of polynomials by families of circuits. And I will not enter into details, but it happens that if you consider these three kinds of devices, you have the same computational power. So either polynomial size circuit, which compute polynomials of polynomial degree, okay, either multiplicatively disjoint circuits, or either logarithmic depth semi-unbounded circuits. In some sense, this is the algebraic equivalent of log CFL. So now, how do we associate polynomials to queries? So in the following way. So we have a structure and the formula, and then we recreate a set of variables with one variable per element of the domain. Okay. And to each query is associated these polynomials, which is the sum for each solution of these entities, and these entities are defined as follow. We take all the coefficients, all the coordinates of the tuples of solution of the queries, and then multiply all the coordinates that appear. So it will be easier to show this on an example. So we have this query. I will not give the formula, but suppose that the result is this one. Okay. Then we build the following polynomials. We have a monomial here with x1, x3, x2, x5, which appear 2 times, 5, 2, 3, 1. Okay. So we are reasoning up to permutation. Okay. So we have these monomials. We have a monomials here, x1 square, x2, x3, here, x1, 3, x2, and this one. So the number of, some remarks on the polynomial, the number of variables is equal to the number of elements in the domain. The polynomial is homogeneous of degree equal to the 3 variables. Okay. There is no bijective correspondence between solutions of the query and monomials. Okay. And existential quantification in formula does not correspond to projection on some polynomial variables. Okay. Suppose this is clear because it has some importance in the rest. So the following result come quite, it's quite easy to prove. Given an acyclic conjunctive query phi, we can in time polynomial in the size of a query, the size of a formula plus the size of a formula plus the size of a structure, compute a multiplicatively disjoint arithmetic circuit, which itself compute the polynomial. Okay, so we have a query. From this query, we can, in polynomial time, construct a circuit. And this circuit is such that it computes the polynomial, okay, associated to the following. So an immediate corollary is the following. The weighted counting problem associated to a acyclic conjunctive query is computable in polynomial time, because the evaluation in this kind of circuit is polynomial. So I will probably skip the proof. And it is made by an adaptation of, I would say, Yanakakis algorithm, but with some careful adaptation, because we have to compute a multiplicatively disjoint circuit, and so we have to not to overcount variables, for example. Okay, what about the union and intersection of acyclic queries? Okay, not surprisingly, it turns out that if you take the union or the intersection of two acyclic conjunctive queries, even if they are quantifier free, then you can obtain a shortly complete program. Okay, it's not very hard. It's proved by a chain of reduction, starting from circuit SAT to some circuit satisfiability on grids, and then to sharp CQ on a grid, and then to union or conjunction of conjunctive queries. So now we have, except for the quantifier free case, we have only bad news, in the sense that the conjunction of disjunction of two acyclic conjunctive query makes counting hard, and it is the same if we have one existentially quantified variables. But if we have a look at the hardness proof, which shows that adding one existentially quantified variable makes counting for acyclic conjunctive query hard, and if we draw the graph or the hypergraph representing this formula, we have these things. So one existentially quantified variable in the middle of a lot of free variables. So we have a star in some sense. And so the intuition is that probably this is the source of hardness. The number of quantifiers is not the source of hardness. It is the way existential quantifiers are introduced in formulas. So, c'est bon. So we will try to, in the rest of the talk, in 5 or 10 minutes, try to formalize precisely this notion of star, and try to define what are the reasons that makes counting intractable or tractable for quantifier query. So if we are given an hypergraph and a subset of a set of vertices, the S component is simply a sub-hypergraph containing edges between which there are paths not using vertices from S. So to illustrate this notion, given this hypergraph, so there should be, there should be dark and red vertices. No? More? Okay. So this is. So we are trying to find S component of dark vertices which do not uses red vertices to connect to each other. So in this time, the number of S components for this kind of hypergraph is the following. It is 3, because to go from here to here, we have to go through red vertices, that is the free variables. And to go from here to here, we have to go from using free variables also. So for this kind of hypergraph, S car star is the following. The subhypergraph H prime of an hypergraph is a S k star if it is an S component, that is if it is a component of this kind, this one, or this one. And if there exist k vertices belonging to the set S, which more or less form an independent set. And these vertices will be said to form the SK star. So the SK star of an hypergraph is a maximum case such that there is a SK star in H. So taking the example here, we have the S star size of 4 in the sense that the maximal independent set of red vertices in some S component is here. Here we have to choose one of the two. Here we have to choose one of the two. Here. So the quantified star size of the formula is simply the star size of the associated hypergraph. So what are the, let's take some examples. If we consider this formula, What is the quantified star size? It's 1 because what? We have two free variables, but they are both embedded in one atom. So there can be at most, there cannot be an independent set of size more than 1. Okay. If we take path formula, so of arbitrary length, then the quantified star size is equal to 2. Okay. And if we take star formula in this sense, okay, so we have these u variables related to x, y, z, and t, then the quantified star size is the degree of the center of the star. So it happens that if quantified star size is bounded, then evaluation is easy, in the sense that there is, again, an algorithm that, given an acyclic conjunctive query phi, compute an arithmetic circuit which itself compute the polynomial. And the runtime of this algorithm is, in fact, the size of a query to the size of the star size, where k is the quantified star size of phi. So as an immediate corollary, it turns out that there is an algorithm for the counting problems which runs in time depending on the star size of the formula. So in some sense, star size expresses how bits of the result are spread. So to obtain such an algorithm, in some sense, we have to see this gives us the size of the maximal tuples we have to pre-select as free variables, and for which we have to check if they can be extended to a solution. So this is not very hard. But it turns out also that computing S star size also is easy, in the sense that there is a polynomial time algorithm, a cubic polynomial time, which, given an hypergraph and a set of vertices, determines the S star size of the hypergraph. That is, it is easy to show to determine how spread are the free variables in the hypergraph. And finally, just to conclude, we will show that in some sense bounded quantified star size is necessary in the following sense. So we are given a class of hypergraph, so which is called S hypergraph. There are pairs of hypergraph and subsets of vertices. And we say that the counting problem related to some fragment of ACQ is tractable for a class of hypergraph, of S hypergraph, sorry. If for all instances whose associated hypergraph is in the class, then the problem can be solved in polynomial time. So we can derive the following result, assuming that FPT is different from sharp W1, and given G as a recursively enumerable class of acyclic S hypergraph, then the counting problem is polynomial time solvable if and only if the star size of the class is bounded. So you cannot have unbounded star size in your class of hypergraph. So how do we prove this? So the first step, which is not shown here, is to prove that counting problem is already hard on class of K stars in a graph sense. So we consider this kind of pattern for formulas and shows that counting problem for this kind of formulas is hard. Okay. Now we consider an instance of this kind of formula. Okay. And we suppose that there is a class G of unbounded star size for which the counting problem is tractable. And then we embed, okay, it's not easy, but we embed this class of queries into the class here, playing on the fact that the class itself is recursively enumerable. And after this embedding is done, we deduce an efficient algorithm for this class of query, which cannot be true unless FPT is equal to W1. Okay. So as a conclusion, this gives a complete characterization this time of tractability frontier for ACQ, in the sense that there cannot be other polynomial time cases as the one described. Easy evaluation is still true for a lot of measures on hypergraph hypergraphs, such as acyclic guarded cover, generalized hypertruth, and so on. So the results generalize also for generalized hypertruth. The results also extend to generalized hypertruth for what concern query evaluation for counting. And for what concern S-clusters recognitions, the result extends partly in the sense that there are some classes of hypergraphs of like bounded inch tree, cycle cut set, and so on, for which we can recognize in polynomial time independently on k. We can compute the k here, sorry, in polynomial time, and there are some other classes like generalized hypertruth for which the bound is dependent on k. Okay, so it was a rapid tour on counting and enumeration. Last things I can say is that okay, these two results are of very different nature, in the sense that one is charting the tractability. One is charting the frontier between tractable and very tractable. The other one is charting the frontier between tractable and intractable. But they both illustrate the importance of the role of free variables in formulas. Okay, they can be related, but it's out of the scope of this talk. Okay, thanks a lot.
Do you expect there to be a straightforward way to restrict the class of queries that you're considering and get a sharp L complete problem instead of a sharp P complete problem?
Good question. I don't know how to obtain this bound because, as you see, very few changes leads to sharp P complete, and I'm not sure this is a good measure to have a final characterization including sharp NL.
This is a comment, since you're looking at counting. There is a major open problem now for 20 years. What happens if your relations are really multi-sets rather than sets? Then
so you count the number of occurrences?
Then you count the number of occurrences of tuples in the answers as well. And then the major open question is containment over in the model of multisets other than sets.
Yeah.
So the relations are multisets. Every tuple come up with a number of occurrences, and the same thing in the output. And containment means that for every tuple, the number of occurrences has to be a less than relation.
So
that's how you define containment.
Does this mean that it is like a weighted counting problem, but for weights in hyperage?
Well, I mean, it's not just weighted counting, because for every tuple you get a count. Every tuple comes with a count, and you're comparing the count of tuples. You have two queries, you're applying them. Every tuple comes with a count, and you want a lesson relationship between the counts on a tuple by tuple basis. So it's not, you don't get just counting. You get a set of numbers, and you have to compare them. And this has been now open, whether it's decidable or not, for about 20 years, actually, 1992. So I think 20 years now it's been open, whether it's decidable. No non-trivial lower boundary. And part of the process, what reminded me is that you construct polynomials. So we know how to reduce it to Diophantine equations, but not in the other direction, unfortunately.
Here, behind this, but not related to counting, the main major problem is to find a complete problem for the class of polynomials recognizable by polynomial size family of polynomial degree, in a sense. So there are a lot of problems very natural problems for bigger or smaller classes, such like permanent or determinant and so on. But precisely for this class, which is the non-uniform class associated to these problems, there is no complete problem from years now, 20 years now.
Any other questions? Thank you again.